Hello guys, thanks for joining us today. Today we'll be talking about encryption and hashing, why do we need it, and well, what technologies should you use. My name is Danilo Vorotintsev. I'm a senior software engineer in EPAM. I hope that by now you know me from my previous Light talks. So what is encryption in general? It's a means of securing digital data using one or more mathematical techniques with a password, or is it called key, to decrypt the information. Why do you need to protect your data? First, why do you need to encrypt your data? First, it allows you to protect some confidential data. So if you have a bank application, you don't want your hackers to know how much money your clients have. And second, it's required by some standards. For example, there is a standard HIPAA. It's a healthcare related standard. So if you want to create a product for America and you want to sell it there, and you process some health-related information, you have to encrypt data. Otherwise, you will be prosecuted. So yeah, encryption is required, and it's implemented everywhere in today's programming. Encryption appeared several thousand years ago, and here's an example of Caesar cipher. It's one of the oldest ciphers known today. It's quite simple. We take some key, here it's equal to 3, and then we just shift all our letters by that many letters as our key. So A becomes D, B becomes E, C becomes F, and so on and so forth. So using a key 3, text hello world becomes this one. And knowing key, we can revert the encoding, get the original text back. We just need to shift letters in another direction. So instead D, we write A. This cipher was used 2000 years ago, but nowadays it's not used anywhere because it's too simple to crack. Today we will not go into details how you can crack ciphers, but just believe me that it can be done really fast, within milliseconds. Okay, the next question, where do we protect the data? In general, data can be encrypted in 3 different places. First, in transit. When you make any request from one server to another, data can be encrypted while it goes through the wires. Protocols that can be used for it are TLS or SSL and, well, HTTPS. The second place, it can be encrypted at rest when the data is stored on the disk. And an algorithm example is AES 256. We will take a look at it a bit later. And the third place is in use. It's quite a rare case, but some advanced algorithms allow you to perform simple computations on encrypted data without decrypting it back. So, for example, you can just calculate the length of your string, but you cannot perform some complex computations like substrings, etc. Okay, let's go further. There are 2 main encryption types. The first one is symmetric. The same key is used to both encrypt and decrypt the data. So here we have some file that we want to encrypt. We use our secret key and some algorithm, and as a result, we get an encrypted file. Then using the same key, we can decrypt it using maybe another algorithm, and we get our file back. The second type of encryption is asymmetric. It uses different keys to encrypt and decrypt data. There is, the first key is called public because it may not be protected very hard. Public key is used to encrypt the data, and private key is used to decrypt it. Private key is also called the secret key. It should be kept in a secret. You can understand from its name. Secret key is used to decrypt all your data, and if someone gets your secret key, he can decrypt all your data and will get all the information. But if someone gets your public key, all he can do is just encrypt more data. So it's not a threat for your application. You can distribute public key however you want through the internet, etc. Let's take a look at some popular algorithms, both symmetric and asymmetric. One of the easiest symmetric algorithms is the XOR encryption. It's easy to break. It's not used anywhere, but well, it's easy to understand. I have a string in binary form that I want to encrypt. This string is 4 bytes long. Each byte is 8 bits here. And we have a key. My key is very short. It's just 1 byte, just for the sake of presentation. We split our string into chunks of the same size as a key. So here I have 4 chunks, 1 byte each. Then we copy our key, so it matches, its length matches the length of the string that we would like to encrypt. And then we, one by one, start executing XOR command with these bits. So 1 XOR 1 is 0, 0 XOR 1 is 1, etc. And we get an encrypted text. To decrypt it, we execute the exactly same operation. We take our encrypted text, take 4 copies of our key, and execute the same XOR operation. As a result, we get the same string as was our input string. Again, this encryption is not used anywhere. You should not rely on it. If you want to use symmetric encryption, you can use AES algorithms, Advanced Encryption Standard. It's a family of symmetric bulk encryption standards. It includes at least 3 algorithms: AES 128, 192, and 256. The number tells you in what blocks the data is encrypted. So here we encrypt data 1 byte at a time. Here we can encrypt it multiple bytes at a time. Either 128 bits or 192 bits or 256. And also this is bulk encryption. So it means that data is encrypted in bulks, in blocks of the same size as the key. Here is the schema of how this algorithm works. You don't have to memorize it. You don't have to really understand it. Just what I wanted to show you. We have some key, and then we execute 10 rounds of same operations. So we just substitute some bytes, shift rows, mix columns, and add round key, and we do that 10 times. And as a result, we get a ciphertext. To get our plain text back, we execute the reverse of these commands. So we don't shift rows, we inverse shift rows, and we execute these operations 10 times again, and as a result, we get a plain text. AES is considered nowadays a secure algorithm, so yeah, you can use it. Then we have two asymmetric algorithms. The first one, the most popular one, is RSA. It's a symmetric algorithm that relies on the difficulty of factoring problem. Factoring problem, it's just a problem of finding prime multipliers of a number. If I give you a number 15 and ask what are the prime multipliers, you can tell me it's 3 and 5. And yeah, prime numbers are the numbers that are divisible only by 1 and itself. But what if I give you this number? Can you find out what exactly two numbers, this number is a result of multiplication of? There is no simple mathematical algorithm of finding these two numbers, and based on complexity of this task, RSA algorithm is built. And here the number is only 40 digits long, and what if I give you number 100 digits long, what even more? We will not dig into the generation of keys. There is some advanced math applied. What you should know, just that RSA is a symmetric algorithm for encrypting data. If you're interested in how it works internally, you can read Wikipedia. I just copy-pasted it here. The next family of algorithms is a more modern one. These are algorithms built on elliptic curves. These are curves described by an equation y equals x cubed plus ax plus b. So yeah, the graph of this equation is this red line. It's one of possible options. And also we can draw a straight line, and this straight line will have up to 3 intersection points with the curve. That are usually called P, Q, and R. And elliptic curve cryptography relies on the difficulty of finding of these points of intersection when you don't know the exact curve, etc. Mathematics here is even more complex than with RSA. So if you're really interested, you're free to dig into it. But fairly speaking, I don't understand all the math applied here. What we should know, elliptic curve cryptography provides an equivalent level of encryption strength as RSA with a shorter key length. So the speed and security offered by elliptic curves are higher. RSA nowadays requires big keys, well, at least 2 kilobytes long. 4 kilobytes are better, 8 kilobytes are very secure. For elliptic curves, 380 bytes are good enough. So it's like 5 times smaller. Yeah, elliptic curve cryptography is a relatively new group of algorithms, so not all tools support them. But if you want to use them in Java, there are libraries that allow you to use them. Let's compare the two encryption types. First is symmetric, second is asymmetric. Number of keys, single key for encryption and decryption in symmetrical encryption, and 2 keys in asymmetric. Okay. Security. Symmetric encryption is less secure because you use only 1 key. It can be leaked, it can be brute forced maybe. So yeah, it's considered less secure. Asymmetric is much more secure. Key lengths for symmetric encryption, it's yeah, as we saw for AES, it's 128 bits or 256 bits, so relatively short keys. For RSA, 2 kilobytes or more. For elliptic curves, 348 bits is considered enough nowadays. So yeah, for asymmetric, keys are longer. Confidentiality. In symmetric encryption, we have only one key, and there is a chance that this key is compromised when you distribute it. For asymmetric encryption, there are two keys. Public key you can freely send over the internet, use, I don't know, kind of envelope, just simple post envelope to send it. It's all considered secure. So yeah, less chances of compromising the private key. Speed. Symmetric encryption is much faster. I compared some algorithms. They were 10 times faster than elliptic curve. Other algorithms can be even more faster. And yeah, symmetric is much slower. Symmetric encryption can even be implemented on the hardware level, making it even more faster. Even faster, yeah. Algorithms AES or DES, and there is a whole bunch of symmetric encryption algorithms for asymmetric, RSA, and ECC. Data size used with this encryption. Yeah, symmetric is very fast, so it can be used with big chunks of data. So if you want to transmit, I don't know, 1 gigabyte file over the network, you should not use asymmetric encryption. It's very slow, so just use symmetric. And yeah, vice versa, asymmetric is used to transmit small amounts of data. Okay, pretty logical. Resource utilization. Symmetric key works on lower usages of resources, and asymmetric on higher consumption of resources. Okay. Now let's see how TLS works. So what TLS is? It's a protocol that changes HTTP to HTTPS. So it adds a secure component for your internet connection. TLS uses both asymmetric and symmetric encryption. Let's see how it works. So there is you and the server that you want to securely connect to. Let it be MJC.school. Great website if you want to study Java. A minute of commercial. Okay, so you send the request using a secure protocol. So instead of HTTP, you use HTTPS. Server receives your request and it returns you a certificate and its public key. Certificates, it's a thing that is used to prove that this server is really the server that you are trying to connect to. So you get a certificate and the public key. You then have to validate the certificate and the key. So it can appear that you sent your request not to the mjc.school, but to another server that hackers installed and well used our DNS name. Yeah, you validate a certificate and key in a so-called trusted root certificate authority. These are third-party services, servers that keep tracking all the certificates and public keys. And you just send them the certificate and key and ask, are they valid? And it tells you, yes, this is really mjc.school you're trying to connect to. Then you have a server's public key and you agree on the strongest type of encryption that both you and the server support. Then you have to generate a secret key and encrypt it. This secret key will be used for symmetric encryption. You generate it just like a random number. And you encrypt it using public key. Then you send it to the server, and server can decrypt it using its private key. So no one else can decrypt your secret key. If someone catches your request in the middle, intercepts it, he just can get an encrypted secret. Okay, let it be. And yeah, the decrypted secret key can get only the sites you're trying to connect to. Now you both have a secret key, or it's also called a session secret key. And then you could start exchanging data, encrypting it using a secret key and some symmetric algorithm that you agreed on. For example, AES 256. So first, we use asymmetric encryption to exchange our symmetric key, and then we use symmetric key to exchange huge chunks of data. So when you establish a connection, we don't know how much data you want to send us. If we use just the public and private keys, well, it will be too slow. Yeah, a session is established with a asymmetric encryption, and then symmetric encryption is used. If you still have questions, you can post them. I'll try to answer them, explain maybe it one more time. Yeah, you don't have to remember all these steps. They're a bit advanced. Just what you should know, two different types of encryption are used, and certificate that server sent to the user is validated in the trusted root certificate authority. Okay, let's move forward. Best practices when you encrypt data. First, always use data encryption in transit and at rest. So when you send requests and when you store data on disk. There is no real reason not to use these types of encryptions because they're relatively cheap. And in fact, in some places, you cannot disable them. So for example, if you use AWS Cloud, it's an Amazon Cloud where you can rent computers for your application. Encryption at rest is enabled here by default. You cannot disable it. Maybe you can change the algorithm if you don't like the default one, but the data will be encrypted. You can't do anything about it. So yeah, use data encryption in transit and at rest. Use popular algorithms. They're well checked. If you use something new, there can be some kind of shortcuts that can be later used to decrypt your data without the key. So new algorithms are not that reliable. Protect access to your secret keys. If your secret keys leak, well, anyone can read your private data. And don't invent the bicycle. It's better not to implement your own encryption algorithms. They will probably be not so good because well-checked algorithms, the old ones that we should use, were developed by the mathematicians with many years of experience in this field. And many people tried to crack them and they failed. So it's really, really hard to invent something like that. Okay, if you have any questions, please post them. Again, I tell you. Yeah. Let's go further. Let's talk about hashing. This topic is slightly related to the encryption, so I decided to mix them in one light talk. What is hashing? Well, hash functions, you should probably know them by now. Each Java object has a hash code method, so it's basically the same as just simple hashing. Hash functions are the functions that take some input and give you output of the fixed length. Usually hash functions are one way, so you cannot decrypt it. If you get a hash, you cannot understand what object was passed to the hash function. Hash functions have collisions, so you can construct two such objects that will give you the same hash value. And for hash functions often have an avalanche effect. This is a bit more advanced. Let's see how it works. Here is an online example of SHA-256 hashing, and let's input something. Hello world. I have a hash of fixed length. If I add more characters to it, the length of the output doesn't change. Output changes, but not the length of it. Okay. Yeah, there are collisions in SHA-256, but I cannot show you it because I don't remember strings that result in the same hash. It's quite yeah, it's quite complex question, really. Yeah, but what is avalanche effect? It's effect that tells that if we change a single bit in our input, the output changes significantly. So I have a string hello world. Let's change a single bit in this string in its binary representation. I change the last letter to E. And you can see that the whole string changes. So it was for D, and now it's for E. This property makes hash functions more secure, more reliable. Okay. Where hashing is used? It's used in message digests, password verification, and some data structures like hash map. We will not cover hash maps today, so I hope you know how hash map works internally. If not, it's a great reading. Please take a look at it. Let's start with the password verification. So what happens if we store just a plain password in our database? Like, I don't know, Danila has a password of 1234. If someone steals our database, he can understand what was the password of all our users. It's not really good. What can we do? We can hash the passwords. So no one will be able to understand what was your password. If we just stored the hash, not the source, you cannot decrypt it. It's a good first step for securing passwords, but it should not be the last one. The problem with storing passwords just with plain hashes is rainbow tables. So here's an example of rainbow table. It's just a table with something with our something happens to our picture. Yeah, I hope it's okay now. Rainbow table. It's a table with 2 columns, source and hash. And if you steal a database that stores hashed passwords, you can just find the hash in this table and see to which source it matches. So it's pretty simple to make this table, and if you make it for 1 million most popular passwords, you can crack, I don't know, 60-70% of all passwords. What you can do here is you can add salt. Yeah, so the process is called password salt. Salt is a random data that is used as an addition to a password for hashing. So we hash not just the source 1, 2, 3, 4, 5, 6, 7, but we concatenate this string with some salt that we generated, and we get another hash. Yeah. In this case, rainbow table will not help anyone to crack your database because salt is generated randomly. It can be actually much longer than that. No one will have a rainbow table that has all the popular passwords and all possible salts. This table is just too long. It will not fit in memory of any computer. And yeah, you generate a random salt. You can store it in the database near the password hash. And when someone sends you a login request, you take the password that you received, concatenate it with salt again, take a hash again, and you just compare two strings. That is a simple approach, but yeah, not really the best one. Nowadays, well, yeah, if you implement the password protection yourselves, for example, for educational purposes, so password salting is what you should do if you want to protect your passwords well. If you work, for example, in production, it's better to use some modern algorithms. For example, bcrypt. It incorporates salt automatically, protects from rainbow table attacks. You can actually control the speed of algorithm by the rounds parameter. It's just a parameter that specifies how many the hash has to be taken. So if you have one round, you just take a password and hash it. That's it. If you have two rounds, you hash the password and then you hash the hash of the password. And then you can hash this value and hash that value and so on and so forth. If you have many rounds, the speed of algorithm will be relatively low. So it will take a lot of time to check if the password actually matches. This is the way of securing, of preventing brute force attacks. So if I have your database and I can just try to get the password that matches. So I'd like to get your password for some site. I try 1, 2, 3, 4, 5, 6, 7, 8. It doesn't match. Okay, I'll try to add 9. Okay, it didn't work too. I'll try. Yeah, you try all possible strings until you find the real password. If you have many rounds of hashing, then the speed of algorithm is low and it will take too much time to brute force your password. Also, bcrypt, in bcrypt, each hash is different, so check is done not by simple string comparison. If you actually, let's see a demo for that. I have a bcrypt here. Let's input a string. I don't know. It's my secret password. Here we can specify rounds. It's actually not the rounds itself, as far as I remember. It's 2 to this power. It will be actually a number of rounds. So I pressed encrypt and I have a string that starts with $to $. It's just a sign that it's a bcrypt. And yeah, let's actually see the last characters, FBI. I encrypt the same password again and I get another string. So we cannot just compare strings to see if the password actually matches. Some more advanced mathematics has to be applied here. But yeah, you can play with it. Just take a. That's right. Actually, let's take a hash. Let's take a password. Check. It matches. We remove some character. It didn't match. Hooray! Bcrypt works. Yeah, now let's talk about digital signatures. It's another place where hashing can be used. Digital signature is the mathematical scheme for verifying the authenticity of digital messages or documents. Valid digital signature gives the recipient high confidence that the message was created by a known sender and that the message was not altered in transit. So, for example, I would like to, I don't know, send you some document, but you have to verify that I sent you this document, not someone malicious user that wants to wants you to believe that his document is actually mine. So how do we do it? We have to, before we can sign documents, we have to generate two keys, public key and private key. I hope you recognize this pattern. It's asymmetric encryption. But here we use public key for verifying and private key for signing. In just encryption, we used them vice versa. Yeah, okay, so we generate this key in a certificate authority. It's just a third-party service that can generate you the keys. How do we sign the document? We take some document and we hash it. We can use any hash function, for example, SHA-256 that we saw. Hashing is very fast, and you can take the document that is 5 GB long and hash it, well, relatively fast. Then, using your private key, you encode the hash. Only you can know your private key, so no one else can encrypt the hash the same way as you can do it. And then we bundle the file, our encrypted hash and public key, and it becomes a one signed document. We can send this circle to our recipient. Okay, how we validate this circle? We first validate that the public key belongs to someone who, well, tells that he made this document. So if you expect that I will send you a signed document, you can validate that this key belongs to Danilo. Then you decrypt the hash using this public key. So here we have one key used for encryption, the second is used for decryption. Decrypt the hash, then we take the file, hash it again, and compare hash with a decrypted hash. If both hashes match, then you can believe that I sent you this document. If not, well, something is wrong. This is digital signatures. Again, you can ask questions. I will do my best to answer them. Also, hashing can be used to verify that the message was transmitted correctly. So, for example, I would like to download Ubuntu. The file that I will download is really big. It's several gigabytes long. How can I be sure that all bits of this file were transmitted correctly? What if one of them flipped? It was 0 but became 1. My Ubuntu will not work. Maybe it will. Maybe it will have mistakes if it works. So what can we do here is we can take a message digest. When someone uploads a file, he can also upload a hash of this file. So here we can find 256 sums. We can open this file, and depending on the type of Ubuntu that you download, there are 2 different hashes. When you download Ubuntu, you just hash this file again, and you compare if hashes matches. Then the file was downloaded correctly. If not, you can try to download it again. Also, these hashes can protect you from some attacks. For example, if you want to download Ubuntu from another site, not the official distribution, I don't know why you may want it, but for example, you want to use torrents because it's faster for you. You can download Ubuntu from another source, and then you have to compare if both Ubuntu's that you wanted to download and that you actually downloaded if they are the same. You can do it comparing the hashes. So that's probably it from my side. We can switch to questions if you have any.
Yeah, thank you for your presentation. We have some questions in our chat. Let's start with the first one. The first is, are those algorithms applied to all sorts of data?
I don't really understand what do you mean. If you mean types of data, if I got you correctly, but I'm not sure. You encrypt just a binary data. It's a stream of ones and zeros. Encryption algorithms don't know themselves what these data actually means. So it can be a string, picture, integer, big integer, whatever. In that sense, yeah, you can use any algorithm to encrypt any kind of data. Yeah.
Yeah,
But
okay.
yeah, if I didn't get you correctly, please ask another question, clarify what you actually meant.
Yeah, I understand it the same way. So I agree that it doesn't understand whether it's text or media data. It will encrypt anyway. The next question is this certificate is used to deliver each frame or just to establish a connection?
I think that it's a question about HTTPS. Yes, certificate and asymmetric encryption are used only to establish a connection because they are slower than symmetric.
Okay, sorry, something wrong with your camera. Could you please reshare?
Yeah,
Mhm.
I'll try, but on my side I see it. Yeah, I reshared.
Still don't.
Let's try to finish.
Yeah, okay. Next question. How is it used in Message Digest? I didn't quite get. Maybe you.
I think I answered. Yeah, I think it's a question about hashing, and I think that I answered it with an example on Ubuntu.
Yeah, one more question is how do you implement password salting in Java?
Well, actually, I didn't do it in a few years. I think there are many libraries that you can use, but if you want to do it just with your hands, you have to generate some random strings. You can see Java dot lang dot I think class. You can save it to the database with your and combine two strings using plus uh,
Sorry, it looks like something wrong with the connection. Let's answer the last question one more time. Danila, can you hear me?
yeah, I can.
Yeah, about salting in Java.
Yeah, sure. I'm sure there are several libraries that you can use, but I don't know them. I cannot name them. But you can use plain Java random class to generate salt of any length that you need, and then concatenate strings using simple Java strings concatenation with plus before hashing the string.
Yeah. Okay, thank you. And yeah, maybe one more last question. From my understanding, encryption happens on the network itself, right?
It means, well, what do you mean by network itself? You in your application, yeah, you don't have to encrypt anything. It's done underneath, but it's well, it's Java has to encrypt it, or operating system. Well, it doesn't really matter. You don't have to do it with your hands. You don't have to set up it, but over the internet, I meant. I still don't quite get. Well, when you transmit data over some wires, wires cannot encrypt the data. Some server has to do it with a computational power. So it's either your server or you send your data to, well, in an unprotected way to another server in your network, and then it gets encrypted on that server. It doesn't really matter, but encryption happens on some server.
Okay, I hope that that answers the question. If we don't have any other, I think we can end our stream. So thank you, Danila, again for your presentation, and thank you everyone for joining us today.
Thank you. Bye.